going to go away. And then this side, e to the 0 is 1. So now what we have is a new quadratic equation, don't we? This is a new quadratic equation. It's not this one. It's different because we have a 1 on this side. So I'm just going to subtract 1 on both sides. Go with me? Now we go try and solve that. And it doesn't factor. That doesn't factor. So you have to use quadratic formula. And maybe we have answers, maybe we don't. Let's see. So what was the quick check we could use to see if we had them? Just do this thing. So it was b squared is 9 minus 4 times a, which is 1 times c, which is 1. That's going to turn out to be a positive number. I have answers. I have 2 x-intercepts. So I've got to go get them. X is equal to negative b plus or minus the square root of b squared minus 4 times a times c. Y'all know what I'm doing or not? Yes? Okay, I don't feel like going and doing that work. You got them? You got both of them? Yeah. Okay, what do we have? These are x. X is 2.618. Let's just go with 2.6, okay? We'll just round it 1 decimal. Okay. And then the other one? 0.38. Or, yeah, we'll just go with that. All right? We trust those answers? She doesn't trust us, so do we trust? Okay, so we should be okay with it? All right. We okay with that? We have 2 x-intercepts. All right, do we have any y-intercepts? Let me ask you this. From this information right here, in the domain, right here, should we have a y-intercept?
No. The zero's undefined.
Where does my graph exist? It exists to the left of 1 and to the right of 2. Okay, to the left of 1 is the y-axis, isn't it? So I should have something over there. So I should have a y-intercept. Does that make sense? Now we have to figure out what it is. I'm just asking you to think about it. What about the y-intercept? How do we get it? You set x to 0, so we were trying to find f of 0. And f of 0 is natural log of, what does it turn out to be up there? Natural log of 2, which is some decimal. What is natural log of 2 on the calculator? 0.69? All right. Making way here. 3. We're going to skip 3. And the reason why I'm skipping 3 is because my domain isn't going to allow for symmetry. Just think about the domain. If your picture is only going to be, like if your picture of your graph can only be here and here, right? Here's 0, my y-axis. Like let's say it does something like this and then like something like this. Do y'all see that that can't reflect over here? Why not? If that reflects over here, then the missing domain has to reflect over here also, right? Like if something's missing on this side and you reflect it, it's going to have to be missing on this side. So symmetry is not possible here.
If it was just on the y-axis, would it be?
If it was what?
Like if the asymptote was 0, like on the y-axis.
Oh, okay, so like if we had this missing like in the middle,
yeah,
then we could check it. But see, even a natural log function by itself is not symmetric. You just go back to what natural log looks like, right? Like that has no symmetry because you can't reflect. So I'm just going to skip this step. No, you can get a symmetric one. You can. You could do something like natural log of the absolute value of x. And then basically that graph looks like this. It goes like this. So on this side, it's the regular natural log. But now you can plug in negative numbers. So when you plug in negatives, you get like a reflection on the other side. But it's possible. Just we're going to skip it. Look, this step, I say only go after the symmetry if it's something that you, like a polynomial or something that'll be easy to check. We don't absolutely have to have this to draw it. It's just helpful to have it, right? Like if we know it should be symmetric and our picture doesn't turn out symmetric, that's something we want to be aware of. All right, 4, asymptotes. All right, none. Or do we have them? Hold on. Why did I say none? What happened to my nice... I used to get mad about that dirty rag that I had in here. Now I've got napkins. I've been downgraded. Okay, do we have asymptotes? We potentially do. Whenever we have 0 in here, right? Because isn't that where we had the asymptote for the natural log to begin with? So do we know when this thing is 0? Yeah, we did that earlier, right? Back in domain. At 2 and -2, we probably have something, 2 and 1, sorry, 2 and 1. We probably have something going on there because that's where this thing is 0. Does that make sense? So I'm going to put here, for vertical asymptotes, x equals 2 and 1. And I'm putting a little question mark because we're not 100% sure what's going to happen there, but it's definitely something is going on, right? How about horizontal? Limit. Let x go to infinity. So limit x goes to infinity of x squared minus 3x plus 2. So where does that go?
You don't need the natural log part?
Yeah, I do need. I even put the parentheses there for it, but I didn't put the natural log. So what does the inside go to? Infinity, right? Infinity squared. Take away what? Infinity. Wait a minute. Infinity minus infinity? That was an indeterminate form, wasn't it? But the easy way to get around that is just to look at these two as being x times x minus 3. That's what that is, right? So now it becomes infinity times infinity. And now you have infinity plus 2. It's infinity. So as I go out the right, it should go up. And then what about if we go to negative infinity? Does anything change? Because that's x squared, won't you still get positive infinity here? If I go to negative infinity, that'll be positive infinity minus 3 times negative infinity. We're going to have 2 negatives, which will become positive. So now you're going to be positive and positive, so this is also infinite. So at the left side, I'm going to be infinite. I realize I'm doing this fast, okay? I realize that. Step 5, I need to figure out where this thing's going up and down. So why don't you work on the derivatives? Let me go see if I can find a fancier towel to mess with. Hi. Do you have towels for the boards or no? You don't have any? Okay, thank you. All right, derivatives, y'all working on those? Yes?
So when you say that the horizontal asymptote, I'm trying to picture that. You're saying it's infinity.
It really doesn't have one. It's not like flattening out to anything. What's happening is as I go out to the right, my function is going up. And as I go out to the left, my function is also going up. Normally, a horizontal asymptote is where it like flattens out to. Here, we don't really have them unless you want to call infinity an asymptote. Is that am I answering your question? No?
Sort of.
Okay, so like back in college algebra, if you had like rational functions that might do something like this, and then like this would approach some line, or like this way, like the x-axis, those were called horizontal asymptotes. And the way we find them in calculus is we just take these two limits. This limit tells us this way, and that top limit tells us that way. What we've determined is that we don't flatten out. We head to infinity this way, and we head to infinity that way. Does that make sense?
Isn't it supposed to have a line?
Supposed to have a line.
This is asymptote. Isn't it like a
No, it does not. That's what these two answers are telling us, is that we don't flatten out to something.
right.
Like if this was 2, like this came out to be 2, then what we'd be saying is that as we go out to the right and draw it, we should go out and get closer to 2. Yeah. All right, those derivatives. What's the first derivative? 2x minus 3 over x squared minus 3x plus 2. Okay, so the derivative of natural log of something is 1 over it, then times the derivative of what's inside the natural log, and then you just slide that up on top. Did y'all do the second derivative also? Okay, so you started doing the quotient rule like this? Okay, so your first derivative is derivative of natural log of something, which is this. And then we take derivative of that. To get the second derivative, you have to do quotient rule, which gives you this. All right, let's get to work on step 5. Where's our function going up? Where's our function going down? So I take my first derivative, set it equal to 0. Let's also, for a moment, think about where our first derivative doesn't exist. Do we have any issues where the where the first derivative doesn't exist? Yes, whenever the denominator is 0. And where's the denominator 0? At 2 and 1, but those numbers are not in our domain, right? So 2 and 1 are already going to be on my number line to begin with, because they're important points when I start doing my test points. But we need to consider that a little bit here. Now here, this is going to be easy to solve, right? Because fraction can only be 0 if the top is 0. So I just get one answer, 3/2. Set the top to 0. That's my only critical number, or critical point. So here I go. I'm going to draw it. Here's 3/2. Right, so this is what I'm saying. When I do this, you can't just pick any arbitrary test point here, because what's your domain? Everything up to what? To 1, and then everything 2 and, oh, wait a minute then, what is this saying then? This critical number is not in our domain, right? Remember, our graph doesn't even exist here, right? So how can we have a critical number in that region? Does that make sense? So what do we do when we had this? This is similar to a problem we had last class. What do we do when we have no critical points, really, and we have some number line? Pick some points. And since we have like 2 different regions to look at, just pick any 2 arbitrary points, and let's see what we get. So how about 0? That's a good one. And then anything over here. I didn't hear. What? 3? Okay. Thought I heard infinity. I was like, yeah. I mean, you actually could use that. But 0, what happens when I plug 0 into the first derivative? So you can plug it in there or just come back over here. Put 0 right there. What do you get on top? Negative. And then 0 here. What do you get on bottom? Positive. So negative over positive is negative. That tells me my original function is going down over here, right? Now, 3 gets plugged in. So we plug 3 into the top. We get 6 minus 3. It's positive, right? And then 3 here. We should get positive again. So positive over positive is positive. So we are increasing over here. See that? Even though we don't have a critical number, we still have down and up. But we don't have any local minimums, right? This is not a local minimum. First of all, because it's like an entire interval. But even if this was just a single point, that point would have to be in the domain, which it's not. So we have no local minimums here. Local max? None, right? We never go up then down. So for part 6, we have neither thing happening here. All right, second derivative, we need concave up and down. So we got to figure out where this thing is 0 and where it might be undefined. So I have to continue to do some work on this. We never cleaned this up, did we? Let's clean it up now. 2x squared minus 6x plus 4. And then when I put those together, I get 4x squared minus 12x plus 9, I think. Minus 6, okay. Yeah, so that's these, and then I have to distribute a negative through. Then all over the denominator squared. Can you all sense I'm moving fast? Yes, you can? Okay. I need to get a second problem in today, so let's... All right, clean that up. I'm going to be working on part 7 here. So part 7, where's my function concave up? Where's my function concave down? All right, so what is a cleaned up version of my second derivative? Negative 2x squared. Negative 2x squared plus 6x minus what? 5 all over that thing squared, right? All right. I need to know when that is 0, and I need to know when that's undefined. Let's talk about the undefined. That's when this part is 0, right? And that, again, is still 2 and 1. So we still have those 2 interesting points. I'll take care of those when I draw my number line. The top being 0. Is it ever 0? Is the top ever 0? I could do a quick check, couldn't I? Check that radical again. It would be 36 minus 4 times A times C. So what is this? This is root 36 minus 40, isn't it? That's root 36 minus 40, which means that this has an imaginary answer or no real solution, which means that this doesn't have an answer. Right? So we have no critical numbers from the second derivative. Yeah, so we're going to do the same thing we did with the other one. We're going to go 1, we're going to go 2. We know we can't be in here. I picked 2 test points, 0 and 3, and these go into the second derivative.
I have a question.
Yes?
What if we have no domain?
If we have
No domain.
no domain restriction at all, then just pick 1 point.
Okay.
So like what we're doing right here is we're saying, look, the second derivative is never 0, which means that we never have an inflection point, right? We never have the second derivative being 0, which means that we're either always concave up or always concave down, one or the other. But because we have 2 different regions in our domain, we have to check each one. If you didn't have a domain restriction, then whatever it's doing everywhere. So you just pick any test point you want. All right, so 0 is going to go into the second derivative, and I think that's going to be easy to do, right? Because the bottom's always positive, and the top, when we plug 0 in here, we get negative. So that means we are concave down over here. And if we plug in 3, we get the same result, don't we? No, do we? I don't know. I didn't check that. I should have checked it, huh? 3 in here? Let me try it. So -2 and then 3 squared plus 6 times 3 minus 5. So 9, -18 plus 8. Yeah, it's negative still, right? And the bottom is positive, so we got that. All right, we're almost there. Here's where I start to put together the table. So on my table, I'm supposed to put what on my table? All my critical numbers, right? Which I didn't have any. So all I'm going to put is 1 and 2. And here's for F prime, here's for F double prime, and here's F, the one we're looking for. And I should, right away, I should just black this out because that's not part of anything, right? And so now I just use my information. What was the first derivative doing to the left of 1? Wasn't it a down arrow? It was a down arrow. But to the right of 2, it was an up arrow. And then we, on both sides, for my second derivative, we were frowns. Right? And then we get the final part, which is this top part. So what is the top left of that going to look like? Right side of a frown. And this is going to look like left side. All right. Now the picture. Notice I'm including my y-axis here. We don't have a whole lot of information, do we? No. We don't have a whole lot of information. So let's go back to the beginning. We knew the domain, left of here, right of here, so my picture is not going to exist here. We knew that already, but the next part was the x and y-intercepts. Where were my x-intercepts? You told me, you calculated them, right? 2.6. 2.6? So let's say this is 3. 2.6 puts us roughly here, okay? Where was the other one? 0.38. 0.38, which puts me, I don't know, just eyeballing it right there. Those are 2 x-intercepts. Yeah, I'm not going to touch that. All right. Now what? Anything else? Y-intercept? What was our y-intercept? Natural log of 2? 0.69. So if I go, let's say that's 1, 0.69 would be about right there. We didn't have any symmetry. Asymptotes? What about vertical asymptotes? Did we have any? We were thinking at 1 and 2 we were going to have asymptotes because natural log would be undefined there. And natural log, usually dives down. Could dive up if we reflected it, but looks like at 1 I have a vertical asymptote, and at 2 I have a vertical asymptote. What about horizontal? This is where we said it went like out to the left, it should go up, right? And to the right, it should go up. Okay. That's all we got, man. That's all we got. So this is it. We're going to draw it. You ready? To the left of 1, I've got to look like that. But I've got to take into account this asymptote, and to the left, I've got to go up, right? So I'm just going to do this. I've got to make sure I maintain that shape. So it's going to dive down like that, and then to the right, it's just going to go up like that. And on the other side, it's going to basically do the same thing. It's going to dive down, and it's going to go up. That's a whole lot of work for not much of a picture there, right? But that's the graph right there. If you wanted to have a little more accurate picture, you could get some more points, but we don't need it. Look, we don't have inflection points. We don't have local maximums or minimums, right? All we know is this, this function is always concave down. It's decreasing over here. It's increasing over there. There's the picture. We're done. So that took us 20, yeah, 157, right? Yeah, just about. All right, let's look at the graph. Natural log of x squared minus 3x plus 2. And now the window's all messed up because I messed with it earlier. Let's change that back. Let's go negative 10, 10. Not bad, huh? I do think that was a lot of work for that, but, So can you see how, like, in theory right now, somebody hands you any function, you should be able to sketch it using calculus. The derivatives might get horrific, but this is what was used before there were computers. This is the way we graph things. And I hope that in the previous example, I kind of convinced you that, if you type it into a computer, you may not be able to recover all the important things, but with the calculus, it's easy to pick off the important things. I think with this example, we didn't really gain a lot, right? Other than a good exercise in domains and derivatives and all that. Okay, we are at 2:28, so we really don't have a whole lot of time. 10 minutes? Do I want to hear the story now?
Yeah.
Okay, so this table right here has a name, okay? Because I told you, like, you won't find it in a book or anything like that. It's actually called the Babi Method. Yeah, so let me tell you the story. It's called the Babi Method. So I first started teaching calculus, I think the first time I ever taught it was like the year 2000, all right? And I was about the same age as most of my students when I walked into that classroom. So it was really kind of hard to get the respect that I felt like, which I understand, In fact, when I walked into my first class ever, this doesn't need to be on camera. the test on Tuesday. Review-wise, I'll see what I can whip up tonight and the next couple of days. Maybe send an email out to say, hey, take a look at these problems in the book. These are the things you should be emphasizing your studying time on. All right? Just do your homework. Okay, this section is it's fair game now. Okay, this section, what is it, 4-4? Right? Go enjoy the homework for that. It's a lot of work. Have a great weekend, everyone. Oh, your quizzes, if you want them back, I'll put them out here. If you don't want to get them today, you don't have to. Bobby. Hey, Bobby.
Real quick, how do you
Yeah.
get the vertical asymptotes again? You said the